Talk for today then is Howard Elman from University of Maryland.
Okay, is this working? Thank you. I want to thank the organizers for the invitation here. I'm really pleased to be here. And what I'm going to talk about is linear algebra for parameter-dependent PDEs. So I have really three goals in this talk. One is to kind of give a sense of what kind of ideas are out there for solving problems that arise in this setting in parameter-dependent PDEs and how the parameters influence things. I'll also try to give a sense of what contributions I and students and collaborators of mine have made in this direction. And the third thing is to try to convince the statistics side, which I don't generally have as much opportunity to interact with, that we're actually doing something that might be of some use to you, okay? And I'll be very happy to entertain questions on that. So I've been working on topics along these lines for a long time, and this is a list of students and other collaborators that I've worked with. I won't talk about the work with all of these people. In fact, I'll probably only get to the first 3 or 4 results and ideas that I've developed with the first 3 or 4 of this list of people. So here's a here's a summary of the talk, and I'm not in that much of a hurry, and I'm also not that anxious to get through all of it. I'm more concerned with kind of getting the points across. So I'll give a kind of intro of the problem we're interested in, and then I'll talk about some results from about 10-15 years ago, and then the focus of the talk will be on item 3 here, concerned with low rank and reduced order models. And if I have time, I'll talk about aspects of solving nonlinear equations, which also come down in some ways to linear algebra, but they're more interesting or more complicated. So here's the intro material. Okay, we're interested in solving parameter-dependent PDEs. I'll also say that Max actually in his talk later helped me a little bit by summarizing a lot of the things, and I won't say as much about some of those things, but I will reiterate his point that it's very hard to give up x as the variable associated with the spatial discretization. And so somehow to me the parameters feel very different to me. So I haven't called them y, I've given them a different name, c. So throughout this talk, the parameter space is a space defined on, it's an m-dimensional space where m is some parameter that was n in Julia Shariar's talk this morning. I'm calling it m, and those are the parameters that the problem depends on. And we're interested in a PDE up at the top, which is written in just a very generic way here, and we want solutions for many values of the parameter. I will talk about some relatively straightforward PDEs, a diffusion equation. Probably the main focus will be on the diffusion equation. If I have time, I'll talk about the nonlinear Navier-Stokes equations in compressible flow. But parameter-dependent examples of these things arise in many settings, and I'm not claiming in what I'll show today that we know how to solve the much more complex models that people are really interested in, but these are often building blocks in such models, and if we can get insight here, I think we can make use of them. So we are posing our problem on a domain D rather than a domain omega, and with suitable boundary conditions, which I won't worry about. I will assume throughout only that the operators depend on parameters. It's also possible that other things like forcing functions and boundary conditions depend on parameters, and everything I say really is applicable in that setting, and the more challenging issues come up when the operators depend on parameters. Okay, so we're never going to be computing unless we're computing in a finite dimensional space. So although I wrote things a moment ago in terms of a differential operator, we're really concerned with a discrete differential operator. I'm assuming that we've achieved some discretization. It could be finite elements, it could be spectral methods, it could be finite volumes. Whatever your favorite discretization is, you have a discrete algebraic system that you want to solve, which is parameter dependent. And you want to get high resolution, you want to get reasonable accuracy so that it's a good representation of the physical model. So you're going to have, typically, not in every scenario, but often you have large systems to solve. Okay, certainly if you use traditional methods such as finite elements, you're going to have, if you want good resolution in the three-dimensional models, you're going to have a large discrete system to solve for every parameter. And in contemporary computing situations, despite the many increases in computing power, it's always easy to make things too expensive to do this practically. Okay, so we want to instead, in this parameter-dependent setting, we want to construct surrogate discrete solutions. Okay, so the solutions are still going to be, the things we're looking for will still be large in the sense of a spatial discretization, but hopefully much easier to compute than actually solving the problem in order to do simulation. And the whole point here is, this has been mentioned many times in the couple of days already in this meeting, that it's understood for simulation that function evaluation is expensive, and it's too expensive to get a lot of function values. And the idea here is to approach that question and to make it less expensive to do function evaluations. And I'm hoping to convince you that in some ways the evaluation of the surrogates instead of evaluation of the solution is dirt cheap in comparison to the function evaluation, which is not to say that it's free, because again, the problems are going to be large, and you're perhaps talking about spatial resolution with hundreds of thousands or millions of degrees of freedom, but much cheaper than resolving a problem every time. Okay, so then the point of view that I'll have in discussing this is that the surrogate solution that we're looking for is going to be a linear combination or sum of separated terms which involve vectors in the sense of there being the coefficients of some solution discretization multiplied by some parameter-dependent functions. Okay, so the vectors could be finite element coefficients or finite difference or finite volume discretization values, and the parameter-dependent functions are basis functions in a parameter space. Okay, such as, for example, polynomial chaos if we're using a stochastic Galerkin formulation, which Max spoke about yesterday, or Lagrange interpolating polynomials if we're looking at stochastic collocation. So doing the simulation will involve a so-called pre-processing step, which is in some settings called an offline computation. We'll get these once, these spatial vectors, and then to do the simulation, we'll do Monte Carlo, for example, on the surrogate function. And again, just to restate this one more time, once we have these required solutions, or equivalently, it will be convenient to think about these collection of solutions as being put into a matrix of order nx, which is the size of the spatial discretization, times nc, which is the number of, which is a size of a parameter discretization. Okay, then simulation will be cheap, and it involves essentially a matrix vector product u by the values of these functions evaluated at the given parameter. And in addition, a large part of the talk that I'll be focused on is to achieve further savings by introducing the idea that these solutions that we're looking for actually have low rank. So this is going to be the outer product of a long thin matrix times a short wide matrix. Okay, so I'm going to focus on a simple representation of the coefficient that appears, for example, as a diffusion coefficient, which in this case is linear. I can actually consider slight affine extensions of this where these are not linear but simple functions of these parameters as the coefficient, as the input. Okay, so the Karhuna-Love expansion looks like that. A layered representation of a domain will look like this. It's actually possible to represent reasonable approximations to log normal terms in finite sums of this type My focus on discussing things will be on the stochastic Galerkin method, but before I get to that, I'll try to give you some idea that it's really quite general. So when we discretize a problem that has this as a coefficient, we end up with a linear system of equations that has a Kronecker structure. Okay, so it's spatially discrete matrices times matrices in the parameter space, which, if we assume, as is typically done, that the terms in the parameter space are the random variables associated with the parameter space are independent, then these matrices will be sparse. And the solution we're going to look for in this case is going to be a stacked version of the data that I was talking about a moment ago. This is a long vector of order nx, each component, times nc. Now, it turns out that, well, this is the way these ideas were looked at for a long time, but it turns out that there's an equivalent, quote, matricized form of this equation, which looks like this. And this is a kind of classic result that you find in linear algebra textbooks. There's a textbook by Horn and Johnson, which describes the relationship. And once you get used to it, there's a little interesting thing, which is to try to remember the order in which things appear. They appear in the opposite order, okay? So when there's a Kronecker product of matrices of this type, there's a matrix product of this type where the A comes first rather than second, and the G comes second. So I will take advantage of this structure. And a classic problem that has structure with just two terms is Lyapunov equations. Okay, as I said, I'm going to kind of focus on the stochastic Galerkin finite element method for generating example problems, but we're not limited to that. And in particular, these ideas are applicable to the stochastic collocation method, because in that case, we're going to sample values at interpolating functions, and all we have to do that is to take a diagonal matrix consisting of the we're going to have how do I want to say? We have NC sample parameters from the sparse grids, and we take the ELF component of that and create a diagonal matrix of that type, and then we have the exact same form of the matrix for the collocation discretization. And in fact, we have the same form for Monte Carlo. It's a little less clear in the case of Monte Carlo because one thinks of taking a lot of samples from Monte Carlo rather than a small number. But nevertheless, at least formally, this form is still true in general. Okay, so it's a quite general form. And we're going to take advantage of that. And for all of these forms, we're going to be also looking at low-rank solutions of this problem. Low rank in the sense of the rank of U. Okay, so let me talk for a few minutes about my early efforts in this direction, which involves, so the solvers that I'm going to be talking about are kind of, I wanted to say this earlier, the techniques that I'm going to talk about in this talk are all classical techniques of linear algebra. Elementary in many ways. It's the type of thing you might see in a first course in numerical analysis in a graduate program in applied math, or in my case, computer science. And so the methods are going to be Krylov subspace methods, such as the conjugate gradient method, and multigrid, and these are both, sparse matrix or PDE-oriented type of ideas. And in addition, very classic methods of numerical linear algebra, such as QR factorizations of dense matrices and singular value decompositions, which you all using, as you well know, when you do the POD or PCA. Okay, so my first efforts in this direction were to examine some multigrid methods, and I only want to just go through this very briefly. These are ideas from about 10 years ago. Classic multigrid just goes like this. You have a fine grid operator and a coarse grid operator. Now in our Kronecker form, we have versions of those for every component of our matrix, and this is what multigrid looks like. We do some smoothing. We do a restriction to a coarse grid. We do a coarse grid solve in a two-grid method, and then we do a prolongation to the fine grid, and we update. And the error analysis of multigrid, so the way multigrid works is that you smooth out oscillatory components of the error on the fine grid, and then the solution is well represented then on the coarser grid, and you can solve that more cheaply, or you can do it recursively and smooth out again on the coarser grid. And a convergence analysis is based on looking at the error operator, and it's not really that important that you focus on this particular matrix. The classic error analysis of multigrid, which is due to Hackbush, separates out a so-called approximation property, which says, in essence, that the smooth modes on the coarse, the smooth mode, the eigenvalues associated with smooth modes on the coarse grid are well, the eigenvalues of the smooth modes on the fine grid are well approximated by the eigenvalues on the coarse grid, and the smoothing property says we can make things smooth on the fine grid for the oscillatory modes. And this work was with a graduate student, Darren Furnival, and the hard thing of doing, so we showed that you get textbook multigrid convergence, and the way to do it was to basically introduce a semi-discrete space, which is continuous in the spatial component and discrete in the stochastic or parameter component, and do the type of error bound that one gets for classic multigrid on the semi-discrete space, and apply that for every realization on the semi-discrete space, and then the analysis of classic multigrid applies, and you get grid-independent convergence. To be completely honest, to do this, we're not doing anything multi-level in the parameter space, and to do this in multigrid requires a matrix computation on a space equal in dimension to the size of the parameter space. If that space is of a size million, then this is not going to be a very effective method. If you have say 5 to 10 parameters and polynomial degree and polynomial chaos of degree 3, 4, 5, something in that range, then the size of these problems is on the order of several hundred, and that is in contemporary computing is basically free. In MATLAB, it's a backslash, and it takes 1/10 of a second. So textbook multigrid convergence. There's another project which I did with Catherine Powell, which is to here's one more time right here is the matrix that is the coefficient matrix of interest, and if we think of this as being a perturbation of this operator, which is the mean operator, we can use the mean as a preconditioner for the coefficient matrix. And better than that, use multigrid as an approximation for the action of the inverse of the mean operator. These are separated in the stochastic Galerkin formulation. This is an identity matrix, so this is just a collection of independent, discrete, in the case of diffusion equation, Laplacians, and you can easily apply the action of the inverse of that effectively using multigrid. And we also have a convergence bound, which gives textbook convergence of multigrid, grid independence convergence. The two methods, they're both effective. This method is a little bit easier to implement because it doesn't involve, it's less intrusive in essence. But these are just a sense of how one attacks the types of problems that arise in this setting. They're not as they're not as difficult as one might think. In fact, the way I got started myself in this business was that this large matrix that was causing people, they were worried about it, was pointed to me by Ivo Babushka, who had done, as you well know, some of the early work in this direction. He said, this is something you might find interesting. He didn't want to worry about it, but he said, you might find this interesting. And I did. So that's background. So now let me focus on the more recent developments, which are concerned with low rank. We didn't take any advantage of the features of the solution in this case. The solution, in essence, from my perspective, is just this big nx by nc matrix. I'm taking the point of view that nx has to be large because we want resolution. nc, we hope we can get away with being not massive, okay, perhaps on the order of several hundred. So here's the matricized system one more time, and there's been some work by a number of people in the last 5 years or so where it was observed that, in fact, when you solve these types of problems, you get solutions that are of low rank, okay? And the actual rank that or they're well approximated by matrices of low rank, okay? So this is the solution matrix. The actual rank, on the one hand, is generally not going to be known. It depends on smoothness criteria. It depends on how smooth the dependence on the parameters are. But empirically, you find that the ranks are often pretty low. So for example, in one little test that a student of mine did, we computed a solution on a grid size of size 16,000, relatively small parameter space discretization. I haven't really said, but this is in essence the size of sigma in the covariance function that was used to generate the KL expansion. So we looked at small, medium, and large values of that size, okay? And this is a plot of the singular values of the solution in this case. So the largest one is on the order of 10, and this is the decay of the singular values. And so for example, if you have a relatively modest perturbation, then you can get a decay of the singular values that's on the order of approaching 10 to the 6, okay, which is kind of my benchmark, with a rank of size about 25, okay? For a larger perturbation, the rank is closer to about 70 or something like that. So instead of looking for this solution, look for these factors, okay? We don't know what they are, okay? But if the right-hand side is coming from a deterministic function, then the right-hand side in this matricized form is actually going to be of rank 1, okay? So initially, when you start doing something like an iteration, like the conjugate gradient method as you go, the ranks are going to be small, okay? We're going to look for something that's of rank perhaps 25, 40, 50, something like that. We don't know what's going to happen as we go, but that's what we're looking for. And initially, we can start with something of very low rank. Initially, as we perform a solve, as we iterate. Okay, so ideas that are now have been out there for some time. The first paper that I know of is by Daniel Kresner, is to apply a Krylov subspace method, such as the conjugate gradient method, to the same type of problem that we were just looking at before, but now try to keep the ranks fixed or low as you go. So the way that's done is to construct iterates that are forced to be in low rank format. Now they're not generally going to stay in low rank format, and that's a negative aspect of this idea. And so, but before I worry about that, if I have something in low rank format and I'm looking at things with this matrix structure, then the matrix vector products that you need to do when you apply a solver of this time can be done more cheaply, okay? Because this is, instead of being this large matrix, it's a product of smaller matrices, and we can perform the matrix vector product separately and reduce the cost of that operation from at least one step of them, one component of it, from order nx times nc times something of order nx plus nc times the rank, okay? If the rank is 20 and nc is 500 and nx is 16,000, then this is going to be much cheaper than this. There's a sum of these things, though, so the number of parameters shouldn't get too big either, okay? So we're not claiming we have methods for solving parameter-dependent problems with 100,000 parameters. We're talking about 10, perhaps 50. But there's one downside here, which is that doing this sum tends to increase the rank. If you take a sum of a rank K matrix with a sum of another rank K matrix, you might double the rank and make it rank 2K. You don't know what's going to happen. It might not be as big as 2K, but it tends to increase, okay? And without writing the details of the algorithm in great detail, you know, there are many sums of this type. There's a sum in the matrix vector product. There's a sum in Krylov subspace methods in which things are updated. Every time you do a sum like that, you're increasing the rank, and that's a problem, okay? So the idea that was in this paper by Kresner is to rank compression, okay? Take this potentially increased rank object and force it to be smaller by looking, loosely speaking, looking at the singular value decomposition of that quantity and throwing away the small singular values and the small singular vectors and forcing the rank to be small at every step, So if I look at the matrix vector product, for example, this is what one would like. This is the result of the matrix vector product. It has, each component has rank something, nr. If there are m terms of them, and m is not too big, the total sum is at most of rank, because there's a 0 in the sum, there's m plus 1 times nr. And compute an SVD, and throw away the old data, and work with something of reduced rank. SVD is not cheap, okay, however. So idea in Kresner's paper is to say, fine, we're not going to compute the SVD of this thing. The singular values can be identified by computing a QR factorization of the matrices before we do the product, okay, and then do the product, but only compute, it turns out the singular values can be obtained by looking at the singular values of a small internal matrix, okay. So this is a QR factorization of order nx times nr, okay? So nr is small, so we can compute the SVD of this smaller matrix and perhaps throw some of them away. This is not free, but it's cheaper than computing the whole singular value decomposition. So this is a method that's now been out there, and it's been shown to work by a number of people empirically, okay? So you compute, you get away, you gain something by computing singular values of a small matrix. You do this rank compression, and there are various strategies for how you throw things out, and I'm not going to get into any of the details of that. And then the one aspect of this is when you do this, you're no longer solving your problem with the classic method, the conjugate gradient method, which depends on very delicate relationships among the data that's being computed. You're approximating that data. You no longer have orthogonality from step to step. Because of that, it's impossible, at least so far as I know, to analyze convergence properties, but it's been shown empirically to work in essence as well as not throwing away the low rank, the small singular values. But it does shift some costs to truncation, okay? This rank compression is not free, and it incurs some cost. These are good ideas, in my opinion. And so we read some of these papers, and then I had a new student, and I suggested to him that we explore multigrid as an alternative. The advantage of multigrid compared to these other solvers is that it's a linear operator. It doesn't, and linear operators, as opposed to nonlinear things involving inner products, linear operators are easier to analyze. And what can we do with this? So here's multigrid one more time, okay? Smooth, compute the residual, restrict. This is the same method as I described on the first slide, just written in more detail, okay? But now we're going to do multigrid with a new wrinkle. We're going to, every time we sum something, we're going to apply some rank reduction operation, okay? Every time we do a sum, every time we do a matrix vector product, we're going to do a truncation, okay? And in the course of doing this, we found that it's helpful to truncate in different ways, but I'm not going to worry about that for this talk. Okay, and I just will cite and say a few words about the fact that, in fact, for this algorithm, there's a convergence analysis, which shows that you again get classic textbook multigrid behavior, but only up to the size of the truncation parameter, okay? If you're going to force things to be no smaller than 10 to the minus 6, you can't reduce your error to anything smaller than 10 to the minus 6. And so there are two terms in the multigrid analysis here. One basically builds on the classic analysis, and another has the size of the truncation as an artifact. I'm not going to show a proof of this thing, but let me just kind of give you an idea of how it goes. So when we're doing an iteration, we're computing some number of steps. If we write the error at step I, if we had done multigrid without truncation, we would get an error at step I without truncation, and for that we have a classic result. Now we have a perturbation associated with that, okay? And it turns out you can show that the size of the perturbation can be bounded in terms of some other multigrid type convergence factor plus the truncation parameter. And that is how the analysis goes. And this was this is a student, Teng-Fei Su, who basically did this analysis. He first did the experiments. I said, well, what do you think? Can you get anything with analysis? And he did. Yes.
So for the multigrid, for the mean base, the constants depend heavily on like the variance and how parameters
Yes.
of the system.
Yes.
How does this?
Less so.
Less so.
Less so. So that's the one difference in terms of the bounds for these ideas. But there's at a cost, okay? At the cost of having to solve things associated with a discrete parameter space. Okay, so let me try to give you a sense of how this method works, and also in general, which I hope will give an idea of how these ideas in general all work, okay? So I took a benchmark problem, which is the diffusion equation. Here's a diffusion coefficient, which comes from uniform random variables obtained using an exponential covariance function with different choices of the correlation length, and we vary this correlation length, but in each case we take the number of terms to obtain 95% of the variability. And for the exponential covariance, we have analytic formulas for the actual eigenvalues. I'm ignoring some of the things that Max raised about errors associated with using a discrete covariance function and errors associated with this truncation. I'm more concerned with, once we choose this problem, how costly is it to solve it? And we're looking at polynomial chaos discretization of total degree p equals 3. Total degree. So holes in the grid, okay? Okay, so I'm going to show you two tables of experimental results and just try to give you a sense of what is achieved here. So, and I do want to say a few things about this. So, first let me look at the bottom line, the bottom row of data. Okay, these rows correspond to grid refinement. Okay, for fixed parameter space, different values of the grid. Okay, the spatial discretization grid, and this is the finest grid we looked at. And I'm comparing here now using the multigrid method without any truncation to using the multigrid with truncation. And what we did is we truncated. We used a truncation parameter. We got as an accurate solution as we could get. And this is how many iterations were required. These were the ranks of the operator for somewhat finer truncation tolerance or somewhat milder truncation tolerance. Milder truncation tolerance costs less to get. The error is only on the order of 10 to the minus 4. The rank of the solution we're looking for, that we found, is 3 instead of 364. And these are the differences in costs. Okay, CPU. Oh, and we chose the stopping tolerance for this to be commensurate with the error we achieved for these. Okay, and these are the costs. So, in particular, if I look at the best cost here, the cost is of 200 times cheaper. Okay, and if I am a little more strict, it's no longer 200 times. It's 100 times cheaper. Okay. But only for the fine grid. If I look at a coarser grid, then the costs are comparable. And the overhead of doing this QR factorization plays a role in this, okay? In fact, let me show you the other data item here, which is for different choices of the size of the perturbation, the sigma in front of the covariance operator for a fixed grid size. This was a 128 by 128 grid. This is the we were a little unhappy with this being the one that looked the best because the numbers get more comparable, okay, once we increase the size of the perturbation. Although if I refine the grid, I can make them look better, but this is what happens. And what I want to show here is in parens now, this is the time to do the QR factorization, to do the truncation. So this occupies 65% or something in that range of the total cost. If I could drive that down, then the results would be better. Okay, but that's a piece of overhead that we don't know how to avoid. Okay, and so for example, there are ideas out there of doing randomized QR factorizations in SVDs rather than actual SVDs, and we didn't find they helped very much, at least in this setting. But it was interesting to me, because I was trained kind of in this way, that these ideas, QR factorization, they're really important, okay? And they're old, no one likes to teach this material anymore, but nevertheless, it's important. And there's another thing I want to say about this, which pertains to the, I want to sell these ideas a little bit to all the applications people now, if I may, okay? Function evaluations are expensive, okay? I am not actually even evaluating the function evaluations here. These are the costs of generating the surrogates, okay? Once I have these surrogates in my hands, if I want to do a function evaluation, all I need to do is evaluate these basis functions, what I was calling psi, okay? The polynomial chaos or the Lagrange interpolants, whatever I have, okay? I didn't time those things here. We have some timings, but not in this study. They are 1% of these times, okay? So this factor of, if I just may sound like a soft soap salesman. I could have used that salesman actually in my apartment. It's another factor of 100. Okay. Now, again, I don't want to claim that we know if you're modeling aerosol, okay, that we know how to reduce the cost of function evaluation by 2000. Okay, that would be absurd. Okay, but the point is, the ideas are there, but now we have these building blocks, okay? Now we need to go back to these codes, which are legacy, and try to somehow make use of them in a way that perhaps can reduce the cost of function evaluations. So these are the costs of what are typically referred to as the offline computations. We're willing to invest some time, and the time we're willing to invest now has been reduced in order to get these surrogate functions, and then we can evaluate these surrogate functions if we can restructure our codes in order to do that. Okay. These are computational solvers that try to find low-rank solutions, and I want to kind of compare them with another approach which I also think is very good, called reduced order models, okay, which I learned about in some work by a large number of people, paper by Tony Patterer and all these other authors. There are now 2 books on this subject that came out last year, one by this group, one by this group. The books are both good, okay? If you want to learn about reduced order models, buy either one, okay? Here's our coefficient. Now I have a slightly more general form, but only slightly more, okay, of the coefficient. Here's a discrete system. Here's how reduced order models are designed, okay? Compute a set of snapshot solutions, some number of them, associated with particular choices of the parameters, okay? Take the results of, again, these are going to be something like finite element nodal coefficients, pile them into a matrix, and then generate an orthogonal matrix that spans these things using, for example, QR. And now you have a potential surrogate solution which you're going to look for in the space spanned by the snapshots. And you'll define the surrogate solution by a Galerkin condition. You're looking for something in the space spanned by the snapshots. Look at the residual associated with any such potential solution and make it orthogonal to that same space. That's a Galerkin condition. Okay, there are Petrov Galerkin conditions alternatively that may have some interest also. But this is a way of generating solutions, okay, generating surrogate solutions. It's different. It's not done dynamically, the way these rank reduction methods were done. It's done by first computing these snapshots by some way, and there's a standard way that people look at doing that, which are so-called greedy methods. You build the basis. These are offline computations you're willing to invest some time in before you go to the surrogate function evaluation. So typically it's done by, if you have some error indicator, for example, an a posteriori error indicator, if you're sophisticated, or residual, if you're less sophisticated, as I am, then you simply, and you have this learning space, you have this parameter space where you search on, find find the parameter that you have a current version of the reduced basis. Find the parameter that that maximizes the error indicator. If that maximal error is bigger than your user-defined tolerance, then solve the problem for that parameter on the full space rather than reduced space, and augment your reduced basis until this condition no longer is violated, and that gives you a reduced basis for solving problems and generating surrogates. And the way you do that is at every time, now when you do your simulation, at every step you solve a smaller problem of order equal to the size of the reduced basis. And the goal in working with these smaller problems is that the cost of solving them, instead of depending on nx, the millions of degrees of freedom in your spatial discretization, it depends on nr, the size of the reduced basis, which you hope is on the order of 25 or 50 or 70 or something like that. So to simulate, you generate a new system of this type. And by the way, there's some, again, offline computations where you pre-compute things in your matrix sum. And so you never work with any data of size nx, okay? Solve the problem. And for both classes of methods, the tasks are divided between an offline step, the step of computing the results, and an online step, the cost of doing the simulation. In this case, the simulation involves this, hopefully, small solve, okay? I had something else I wanted to say, but now I can't remember. I've looked at these methods also, but I'm not going to do any, I have never done myself a direct comparison. There's some work by Peng Chen and Quarteroni who've done some comparisons of some of these ideas, but I don't have any of my own. Oops. But let me just talk about the comparison between them, just philosophically, okay? The low-ranked methods that I talked about before has a truncation in it that may limit the accuracy, okay? You're going to decide on this epsilon truncation that plays into the cost of your computation, into the computation, and that limits your accuracy. And we have a bound now that shows kind of how it does, okay? However, if you do things this way, the offline computations are really cheap, okay? And the online computations are really cheap, and the offline computations, I think, are probably a little less expensive. Okay, but there is an advantage of the reduced basis methods, which is they have this so-called certification. Okay, you can guarantee, if you choose your learning space, if it's representative of the space of parameters, and you guarantee that on the learning space you're always below a tolerance that is your tolerance, then you can be certain, okay, modulo the accuracy of the training set, that your accuracy is what you want it to be. And that's not a small thing, okay? So, for example, one of the textbooks by Hesthaven, Jan Hesthaven, is called Certified Reduced Basis Methods, and this work by, well, everybody who does this in this direction. But the online step can be the offline step can be extremely expensive. So I think I will have time to say a few words about some of that in a moment. I had a student who did this, explored this thing for the Navier-Stokes equations, and she decided at some point, I know what else I wanted to say. I'd like to go back to that. These times are on my student's Mac, okay, laptop. This is 1 minute and 15 seconds to solve a problem of size 261,000 times 364, okay, on a Mac, okay? So, and these are 2D PDEs, but the point is you can actually solve pretty tough problems this way. So this is for modest accuracy. This was for 6 minutes, okay? Okay, and what made me think of that, because this other student, when she started doing this, found this greedy search strategy to be extremely expensive, okay? It took her a week to do the greedy search. And then the computations, once the greedy search were done, took 15 minutes or something like that. And she didn't want to wait to finish her thesis for the multiple weeks that it was going to take her to generate all this data. So she said, I'm going to generate it in a less sophisticated way. I don't think I'll get into the details. We had a lot of trouble with referees on this, but we pushed and we got it through, okay? And so if you talk to the reduced basis folks, they don't care how long it takes. Let it take a year, okay? If you can then do model, and in fact, they have some pretty impressive results. I went to a session, a SIAM meeting in Boston a year ago, where they were doing really sophisticated models of some of elasticity of shipbuilding and docks in Boston, but it didn't work for this student, okay, because it really took, every time she wanted to generate a new example, it was going to be a week, and she wanted to get on with her life. So, okay, I think this has been pretty technical. I want to just say a little word about this, but since everybody's been making quotes, I'd like to just give you 2 seconds of respite now for a moment and say, there was this famous baseball player, Yogi Berra, who's been mentioned a couple of times, and he had many quotes, okay? Some of you may not have heard of them, but one of the things he said was that about a restaurant, nobody goes there anymore because it's too crowded. And but the one that I really liked of his that is not as commonly cited is that he said he would give his right arm to be ambidextrous. Okay, so 2 words about the Navier-Stokes equations, okay? I only want to just convey the idea without getting into much detail. This was this other student, Virginia Forster's project, okay? Navier-Stokes equations are nonlinear. If you want to do these ideas for nonlinear equations, here's the nonlinear algebraic equation, okay? But now it's nonlinear. And so in contrast, and this is what the nonlinear Navier-Stokes equations would look like, okay, once you discretize. In contrast to linear equations, you can no longer pre-compute everything and work with things of size equal to the reduced basis, because you simply have to evaluate the nonlinear function everywhere, okay? And it's not written, but it's also true of the Jacobian. All the advantages of reduced order models are lost if you do it in a naive way, and so there are these ideas which have been mentioned here called empirical interpolation, which very cleverly avoid evaluating the function at every point, instead evaluating it only at a distinguished set of indices. So for example, if you have a finite element discretization, then the function value at any given point, and function value means the operator, the differential operator, the function value at any given point depends on only nearest neighbors in the finite element grid, and so it's an order 1 computation for each point, and so choose cleverly a distinguished set of points that you're going to evaluate, you're going to interpolate your function at, and use those only to generate something that can be pre-computed, and use that as your reduced order model, okay? So it's different from the standard approach. It's developed by French group, Madej and other people, and then developed separately by Danny Sorensen, who wrote it in a linear algebra style. I only want to call your attention to it, okay? The point being that it's an idea that can be used for nonlinear systems. We're not limited to linear systems. And I don't think, I'm out of time. I'm going to spend just 1 minute. I just want to show one table of results for this, which is for a Navier-Stokes equations with a variable viscosity, which is artificial, okay? We made up this problem. It's just piecewise constant on subdomains, okay? And I don't take this to be a realistic fluid dynamics problem. It's just a simple example of a problem that one can test these ideas with, okay? But I believe that there are, even for problems as simple as this fluid dynamics problem in mantle convection and blood flow, for example, we don't really know what the viscosities really look like. So playing with parameterized versions of them is reasonable, I think. This is not physically so meaningful, but it's enough to generate some data, okay? And I just want to give you an idea of what happens when you do this, okay? So what this student Virginia did was to compare the performance of the empirical interpolation method in terms of accuracy with the performance of the reduced model that doesn't take advantage, that doesn't do this interpolation and instead does an expensive computation. And there's no difference effectively in accuracy. So if I compare these errors, which are residual norms, there's no difference, okay? That was something that we weren't sure would happen, but it happened, okay? We also compared the cost of the CPU time, and it's the same story as what I showed before. Once, I don't know if I have this at hand. Once you refine the grid enough, the reduced order yeah, I do. Once you refine the grid, so in this case, with a 64 by 64 grid, it's a different numbers of parameters depending on the KL, on the subdomain space. Once you right, if the number of parameters gets big, the reduced order model becomes a little more expensive, okay? But if you refine the grid, that changes, okay? So as long as you're going for accurate enough solutions, you can win with reduced order model, but it's not an open and shut case. I think I will stop. There's more on this that I could talk about, but I won't today. And just conclude with say, again, there are many interesting issues that arise from this class of problems, parameter-dependent PDEs. We're only kind of grazing the surface in the sense that there are, much more important and more difficult problems. But it turns out that if you work at it, you can get the classic ideas to do the job. Okay, and that's interesting. In addition, as I've said now, the other classic ideas in linear algebra play a role, okay? You can't ignore them, and it's good to look at it carefully. I think we've really only scratched the surface in the nonlinear setting, okay? I am not too aware of a lot of work done on empirical interpolation methods, for example, for problems harder than the Navier-Stokes equations. I have the idea of applying them, even if you add thermal effects, or if you add, like people I do some work with who are interested in magnetohydrodynamics, and then you have Maxwell's equation coupled with the Navier-Stokes equation. Will they work? I would guess so, but I'm not sure about that. So I think I'll stop there, and thank you for your attention.
Questions?
Thank you very much for advertising these methods, vice versus sort of interpolation. I think it's maybe, if I may, it's one property you didn't say, which I find important, is that what comes out satisfies the governing equation in a weak form for every parameter value, which it doesn't for the interpolation methods, which I find
I see.
a big advantage. But if I may add two questions. So you being a specialist in multigrid, when you were talking about multigrid, why can't you do multigrid on the parameter part? Because you have a hierarchical polynomial base in your case. I mean,
you can. I don't think the benefits are as dramatic, but you can do it. The thing is that if you have a nice distribution, such as uniform, if you have bounded eigenvalues associated with the distribution, then the conditioning associated with the parameter space isn't so bad, so there's not as much of a need, and you can't benefit as much because of that. If you have Gaussians and they go from plus infinity to minus infinity, that's a different story, but there are other issues with that, okay? So if you have, so it's not as important, that's why.
A bit surprised on your claim on the difficulty of or the cost of the reduced basis. So if I understood what is costly is the search phase?
There are two costs. Yes. The search phase is very expensive, okay?
Even in the example, in the simple elliptic case, you were using a posteriori error estimators?
I was using the residual. But the thing is, if you need to do a search, it's expensive, okay? It's just, it's expensive. You're searching, a lot of, you have 2,000 or 3,000 parameters in your learning space, and you're going to go through this every time. It's just costly. And again, these students are working on their laptops. But there's another thing which I didn't emphasize, and that is that the cost of solving the reduced order model, which is generally viewed as being very cheap, may not be that cheap, okay? It depends on the size of the reduced basis, because if you have strong algorithmic technology like multigrid at your disposal for solving the unreduced problem, then the cost of the reduced order model is order n cubed, where n is a small n now, and the other one is order capital N, which is linear in multigrid. And if little n is 250 instead of 30, then that's not free, okay? Because you're doing a direct solve.
I have another comment on how the comparison is a little bit unfair, because in the low rank method you do have a discretization of the parameter space, whereas in the reduced basis method you don't implicitly. I mean, it's implicitly induced by the equation, but you don't explicitly discretize with polynomial chaos of a certain order.
Yeah, it's true. Yeah. Okay. I mean, I don't have any problem with reduced order models. I like them.
No, I'm asking what's the influence of the discretization of your choice of third order degree polynomials?
Yeah, you're absolutely right, okay? You have this advantage of the reduced order model is that you're handling the discretization error directly, okay, by greedy search, okay? And you're not in the other way. You're just going to depend on error bounds or whatever you may have, okay? You're correct. It depends on what you want to pay for, okay? Do you want a Mercedes or do you want a Volkswagen, okay?
So I wanted to come back to this variance and variability. So with multigrid, we know that the standard linear interpolation works very well in a certain range of contrast. And I think with the kind of variances you use in these linear models, you never exceed that contrast. Whereas if you actually have much bigger contrasts, then the multigrid interpolation operators just won't work anymore.
I see.
No, but I'm not talking about discontinuous. I'm talking about the range of variability.
Yeah, I think it's okay also, but...
But you just have to look at the solution. If you look at solutions that come out of the kind of problems you're doing, they have little wrinkles, whereas the real, I mean, the more extreme contrast cases have much steeper gradients, and these are the things that make it hard for multigrid to converge. So I'm not criticizing.
No, I understand.
I'm just wondering whether if you push it to more extreme cases, it will also perform as well.
I mean, I've thought about it in a slightly different context for the convection diffusion operator, where there are issues just like this,
issues,
and you have to pay attention in that case. But I've never had any issues with the diffusion equation, so I don't know.
So I'm completely confused because I'm a statistician. So I'm going to be really naive. Statisticians like parameters.
Yes.
We love parameters. I mean, you usually call them theta, but you've got psi as a parameter.
Yes.
So I'm just getting happy with this parameterized differential equation when you suddenly make it random, this parameter. So supposing I want to differentiate, want to differentiate with this parameter or get some higher order derivatives with respect to the parameter rather than immediately make it random. I mean, can you do the classical sensitivity analysis with this?
I mean, I appreciate the fact that you're confused, because it's, I'm confused also when I'm in your position, okay? And I don't know the answer, to be honest. I don't know. That seems to me what the purpose of having all talk to each other now. So
because if you want a likelihood, you need differential. You want a Jacobian. You want to optimize. You want a differential. You want with respect to the parameters.
Yeah.
But then you make it random, and all you can really do is integrate then, which is rather limiting.
Henry, if I may.
Sorry, I'm being provoked.
No, I'm glad to hear this question. Yeah.
Let me just point out, I mean, we talked about the linear algebra techniques that you need in order to efficiently get your hands on a surrogate.
Yes.
You haven't been emphasizing or focusing on the part that what you have, yours is just part of the story. Once you've got the information you have through the techniques that you described, you have a surrogate model. If you then want to do something with that afterwards for further study, that can be done. If you want to know things about how your approximate solution behaves with respect to the parameters. You can do all sorts of things after that. That's just not what you've been talking about.
Yeah.
Okay, I'm happy then. Good.
One final question, then we'll go for lunch.
Just one comment also on the comparison between low rank and reduced basis. I mean, in principle, you can also do essentially residual error estimation and refinement in a low rank context. If you construct a method like that, you can also control the error basically in any Hilbert space that you choose if you choose the right basis functions.
Yes.
So you can get basically control on the whole error, including discretization. But you always tie to a Hilbert space setting somehow because of the SVD. Whereas in the reduced basis, you aim for L infinity basically in the parameter space. So in some sense, it's more like the norm that you want to control. And I would argue that in the low rank setting, if you do it that way, you actually have better control of the error. But in the Hilbert space, because you really control the, let's say, L2 error rigorously, whereas in the reduced basis setting, you always tie to your training set somehow. You cannot sample everywhere. So in that sense, it's more like a question, I think, of what norm do you want to control the error in.
I mean, this is great. As far as I'm concerned, it's excellent. Okay. No matter what you're doing, in the end, you still have to deal with these problems and solve them. Okay, and that's what I try to do.
Okay, so let's thank Howard again. So we've all got the afternoon off.